Okay, so we're continuing on with chapter 10, and this is 10.2, which is independent and dependent events. So we're looking at more ways to find probability when we start making these events a little more complicated to look at. So here we have probabilities of two different things happening, or three different things happening. We want to know how do we calculate probabilities of multiple things happening. So when we have multiple things happening, we want to know if those things are independent or dependent. So independent events means that the occurrence of one event does not affect the occurrence of the other event. So what does that mean? So let's think of an example. Supposing we have my two events are the probability that I cook today, right? So cooking today is one event, and wearing a rain jacket is my second event. The probability that I cook today, right? If I cook today, that doesn't change if I'm going to wear a rain jacket or not. It doesn't affect that. If I wear a rain jacket, that doesn't affect if I cook today. So because those two events don't affect each other, those are independent events. So that's what we mean by independent, when the occurrence of one event does not affect the occurrence of the other event. When these two events don't have anything to do with each other, they don't affect each other, those are independent events. To calculate that, so the probability of two events happening when they're independent is you take the probability of each one and you just multiply it together. So the probability of A happening multiplied to the probability of B happening is the probability of both of them happening. So, for example, your friend writes a phone number down on a piece of paper and the last three digits get smudged. You decide to randomly just choose numbers for those last three digits. We want to know what is the probability, if guessing the first digit correctly and then guessing the second digit correctly are independent or dependent events. So event A here is guessing the first digit correctly. And event B is guessing the second digit correctly. So the probability of guessing the first digit correctly, well, that is, we have any number from 0 to 9 could be that digit. So we have 10 different possibilities, and one of them is correct. So it's 1 out of 10. Guessing the second digit correctly, again, we have 10 different digits. Guessing one of them correct is 1 out of 10. If we guess the first digit correctly and then the second digit correctly, now we have two different digits to pick from. So we have 100 different possibilities, right? It could be 0, 0, it could be 0, 1, 0, 2, 0, 3, 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 1, 2, 2, 2, 3, 2, 4, and so on. We have 100 different possibilities. And there's only one pair that's correct, right? It's either 0, 1, or it's 5, 6, or it's 8, 9, or 6, 2, right? It's two of those numbers out of 100, but there's only one pair out of 100 pairs. So the probability of getting both correct is 1 out of 100. So now we can check, based on this formula, if they're independent, this formula has to work out. So we know that A and B happening is 1 out of 100. Is that 1/10 times 1/10? Or 1/10 times 1/10 is 1 out of 100. So because that works out, A and B are independent events. The reason we have, so this is something we could have thought of without the math, right? Like if I pick the first digit correctly, that doesn't mean I'm going to pick the second digit correctly or I'm going to pick the second digit wrong. It doesn't have any bearing on each other because phone numbers are random in that way. Right? Now, if these were the first two digits of the phone number, that could probably affect things, right? If I guess knowing area codes, right, the first three digits of a phone number is the area code of that number. So there I probably have a higher probability. If I guess the first digit right, I can probably get the second digit right better than if I didn't know it was the area code. Right? Like, for example, 408 numbers, right? If I guess the full correct, then the second digit is probably a 0. But since this isn't the area code, right? This is the last 3 digits of the number. That's not something that has any relevance to each other. Those are just like random numbers picked out. So guessing that first digit correct of the last 3 numbers doesn't affect how likely I am to get the second digit correctly. So just thinking about this, reasoning through it, I know that these are independent events. The reason we do the math for it is because sometimes they might not be totally independent because of some other thing. Maybe I just have this like really good knowledge of how phone numbers work, or I work at the phone company that gave out the number and I know something more about it. I don't know. There might be some reason why I can guess that number better after that. So that's why we do it mathematically as well, because we can reason through things, but we might be forgetting some reason that someone could get that number right without us reasoning through it. So that's why we do this mathematical check to make sure that it's actually independent or not. This next problem, this one says that we're trying to guess a 3-letter password, and the only possible letters are A, E, I, O, U, and Y. We can use the same letter more than once, right? So we could have a password that's AAA or OOU or EIU, right? It could be any 3 letters. We can repeat letters. So we want to know if the correct password is YOU, what is the probability that we pick that? So here we want to know the probability of picking Y, and then the probability of picking U after that, and the probability of picking, O after that, and then the probability of picking U after that. So the probability of picking Y, we have 6 letters to choose from, and it's one of those. So it's 1 out of 6. And since we can repeat it, the second letter could also be Y. So we still have 6 possibilities, and it's one of them. And the third letter could still be any of those 6, so it's 1 out of 6. So because nothing affected each of these probabilities, they were always 1/6, we know that these are independent events. Picking Y and then O and then U is just multiplying 1/6 times 1/6 times 1/6, which would be 1/216, because these are independent events, right? Picking the first letter correctly does not affect you picking the second letter correctly, and it doesn't affect you picking the third letter correctly. The opposite of independent events are dependent events. So dependent events are if the occurrence of one event affects the occurrence of the other event. And so this is the occurrence of one event affects the occurrence of the other event. So this is something like if my first event is wearing a rain jacket and the second event is it's raining outside. Well, if it's raining outside, then I'm probably going to wear a rain jacket. The fact that it's raining, that event happening, is going to affect me wearing a rain jacket or not. So that could be a dependent event scenario when these probabilities affect each other. When we find that, that's called a conditional probability. So if we want to know the probability of A and B happening when B depends on A, it's similar. We take the probability of A happening, and then we multiply it not to the probability of B, but to the probability of B given that A happened. So what does that mean? So this symbol means probability of B given that A happened. So this is because if we know these events are dependent, that means the probability of the second event happening changes, right? If A happens, it's one probability. And if A doesn't happen, it's a different probability. That's what this dependent thing means, right? If it's raining, then it's probably a higher chance that I'm wearing a rain jacket. If it's not raining, it's a low chance that I'm wearing a rain jacket. And so that probability of me wearing a rain jacket changes based on if it's raining or not. And so that's what this means, that it's just saying that the probability of B here is going to change. It's not like, for example, this one, it's not always 1/6. It's going to be something else sometimes. So let's look at an example of this. So we have 3 white golf balls and 2 yellow golf balls in the bag. For this example, I would highly recommend you actually trying this out physically at home. So if you have 5 balls that you can like differentiate somehow, or if you just take 5 pieces of paper, you just if you can like rip up a sheet of paper into 5 pieces or something, and just label them 3 pieces white and 2 pieces yellow. So let's try to do that. So we have white, 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 yellow, yellow, right? So we have 3 white pieces and 2 yellow pieces. With probability, it really, really helps to have some physical representations of this. If we were in class, I would be showing you this stuff, and it's really hard to do that remotely. So I would highly encourage you to try to do this yourself. So find 5 pieces of paper, and then just label them, 3 of them white, 2 of them yellow. Now, if we pick a white, so we're trying to pick a white ball first and then a white ball second. So event A is picking a white ball. And then event B is also picking a white ball. So if I pick a white ball, right, so if A happens, the probability of A happening is 3 out of 5 different balls. And if I pick any of these white balls, I have 3 different options out of 5 total options. Now, this one is, and this is really after picking white ball for A. So here we want to know the probability that we pick a white ball, given that we've already picked another white ball first, right? Given that A happened. So here, if A happened, if I picked a white ball, now you remove one of your white balls. Now you only have 2 white balls left. So this probability is 2 out of 4 balls now. So see how the probability changed there? That's what this dependent event means. So this is a dependent event because the probability changes. And now if we want the probability of this happening, we would do probability of A times the probability of B given that A happened, which is 3/5 times 2/4, which is 6/20. Hopefully that makes a little sense. Try to do this out with pieces of paper or balls at home to see this for yourself. And the main thing you're noticing here is that this changes the probability from 3/5 to 2/4 because A already happened. If A didn't happen, then this would be, right, if A does not happen, then we'd have 4 balls, but it would be 3 out of 4 because if we didn't pick a white ball first, then one of the yellow balls went away. So now we'd have 3 out of 4. So these two things are different probabilities depending on if A happened or not. That's what makes this dependent. Let's try a different example. So here we're trying to guess a 3-letter password where, again, the only letters are A, E, I, O, U, and Y. But here we cannot repeat the letters. So now we want to know what's the probability we picked the password A, I, E. So if the probability of picking A first, I have 6 different possibilities, so 1 out of 6 of them. Then I want to know the probability of picking I, but I know I've already picked A. So now, if I had A, E, I, O, U, and Y, I've already picked A. I only have 5 different letters to choose from, so this is a 1/5 probability. And then I want to pick the letter E, but I've already picked A and I've already picked I. So now I only have 4 to pick from. So I have 1 out of 4 to pick that 3rd letter. This is because we can't use the letters more than once. So once I've used the letter, once I've guessed it correctly, I know that I'm never going to have to use that letter again. That reduces the number of possibilities I have each time. And so then this probability of getting all the letters would be 1/6 times 1/5 times 1/4, which is 1 out of 120 chance. This last one is looking, again, sort of a dependent thing. We're looking at an inspector who's looking at defective parts in a workshop, factory kind of thing. So this is kind of like when factories are manufacturing things, they'll inspect their products, right? Like, does this product work or is it defective? And hopefully they catch all the defective things in the factory to make sure, and this is what quality control does at a factory. But sometimes you get things that are defective but still pass the test, or things that, and that's how you get, right? Like you have, sometimes you buy something and it's defective and you have to go return it that the factory didn't catch. And sometimes it's perfectly valid things, they work, but for some reason the test fails. So this table tells us if a part was defective, how many of them passed even though they were defective and how many of them failed. And if they're not defective, how many of them pass and how many of them still are failing even if there's nothing wrong with them. So we want to know, what is the probability that a defective part passes? So event A here is that it's a defective part, and event B is that it passes. So the probability of A that it's defective, well, we have 29 defective pieces out of, so one thing that helps on this is to add up all of these values. So 5 plus 24, there are 29 defective, there are 217 not defective, 213 things that passed, 33 things that failed, and then in total, there were 246 things that were tested totally. So the probability of A, the defective, is 29 over 246. And then for passing, it's 200. If we know it's defective already, well, only 5 defective pieces passed out of 29 defective pieces. And so the probability of B, given that we know A happened, given that we know it's already defective, is 5 over 29. And so the probability of A and B would be 29 over 246 times 5 over 29, which is 5 out of 246. Now we want to know, what's the probability that a not defective part passes? So now A is that it's non-defective, and B is that it passes. So probability of A, if it's not defective, we have 217 of them out of 246. And then for it passing, given that it's not defective, well, 208 passed out of the 217 not defective things. And so the probability of A and B is 217 over 246 times 208 over 217. 217's cancel, we get 208 over 246. Not reducing this for now, I just want you to focus on getting this concept correct. And then that last bit, you can either type in your calculator or reduce the fraction down and then get the decimal for it. Let's leave this for now. Really just focus on knowing if events are independent or dependent, and then being able to calculate these probabilities. That's going to be a lot for this week already, and then we'll move on to trying to expand on this next week. But I want to give you a chance to practice this stuff, especially if probably wasn't something you focused on a lot last year, then this can be pretty challenging and very different to the other types of math we've done in this class. So try to really focus on this, work on it. Again, try to do this, like make these things out physically for yourself and try to see it for yourself. Try to look at different videos online too that might explain this differently than what I did. I can try to find a few more videos to post optionally for you to watch, just to help out. I'm not sure that probably is very difficult for me to think about how to explain remotely, because I'm very, when I teach probability, I usually do it with a lot of demonstrations in class, which I can't really do right now. So I want to try to find as many ways for you to engage with this and understand this more. Hopefully this was helpful. I would encourage you to read through the textbook sections as well, so you have another explanation of it. And again, I'll try to find some other videos from other people as well that can help you. And hopefully with all of that, you'll be able to get through this content.